So in this slide, I just wanted to go over again the stereochemistry of E2 reactions. So what we've said is in E2 reactions, so if we were to draw the substrate as you have on one of your slides, so let's imagine we've got a molecule, it's got a hydrogen, it's got a leaving group, we're going to call the leaving group Y in this case, and we've got different substituents at each end. So this is the sort of carbon-carbon area where we're going to make the double bond. What we're saying is when we do the elimination, you could have these opposite each other in that way. So these are what we call anti-periplanar. So they're planar because they're in the same plane, and they're anti because this bond here is opposite to this one. That one's up, that one's down. So we could do elimination from that, but there's also another way in which we could draw this molecule so that the groups are still periplanar, they're still in the same plane. So this could be another way in which we could have the groups so that they are planar, but now these are on the same side. So these are not anti-periplanar, these are syn-periplanar. So we said for E2, what we need is for the groups to be periplanar, and we've said it's better if they're anti. So it's better if they're opposite each other rather than on the same side. And that's because when our base comes along, if it was to attack here, push the electrons in, it's E2, so all of this happens at the same time. When this happens, what you find is you've got less steric interaction when the base attacks from here and this then departs opposite compared to here. If we were to look, base attacking, feeding electrons, you can see there's a lot of interaction here. The base with the hydrogen, with the Y, they're all trying to occupy the same area of space. So this is going to be less favoured because there's more steric interaction. This one here is going to be favoured because the base and the Y minus are away from each other. So sometimes we draw these using Newman projections. So Newman projection is just basically, if we imagine looking along the bond, what do we see? So if we were to look along this bond, at the front of us we'd have hydrogen R and R1. So we'd have hydrogen R and R1. And behind us, if we were looking along this bond, we'd see the Y pointing down. So if we have a circle here to sort of show that's the front carbon, we'd have the Y pointing down, and if we were to look along there, we would see the R2 between the H and the R. We'd see the R3 between the H and the R1. And this is quite a nice way of drawing this because what it shows is that each of these bonds is lying between the other bonds, so they're not trying to occupy the same area of space, they're what we call staggered. In contrast, if we do the same thing here, so we look along this bond here, so at the front we've still got our hydrogen, we've got our R, we've got our R1. If we were to look along that bond, this hydrogen is directly in front of that Y. So our Y, even as we draw it, we see it becomes a bit awkward. They're trying to occupy the same area of space. Our R1 and our R2 are trying to occupy the same area of space. When we look along this, our R and our R3 is trying to occupy the same area of space. And we call this eclipsed because they are eclipsing, they're directly in front of each other. So the take-home message for this is that for E2, remember it's an E2 reaction we're looking at, the stereochemistry will be influenced by the orientation, and we will go for the anti-periplanar, where each of the bonds is lying between the others in the staggered orientation rather than the syn-periplanar. And that means when our base pulls off the hydrogen, kicks the electrons in, lose the Y minus, we're going to get a defined stereochemistry in the alkene, and that's what we will cover on the next slide.